All right, so this is part two of the multiple regression, single regression analysis. What we did in the last video is we fitted this price variable onto multiple variables of lot size, bedrooms, and driveways. We analyzed these coefficients, analyzed the p-values, and looked at the r-squared because the r-squared increased from the singular regression. And what I'm going to do now is use several components to determine the most ideal multiple regression model based on, the Granger test, the AIC, BIC, the reset test, all of the stuff that I've actually went over before this. So the first thing I want to do is look at the Granger test where I regress just lot size onto price and the reverse. Now, if I try to regress like both lot size and bedrooms and driveway, this is not going to work because Granger test only allows for one variable here as the explanatory variable. But when we do, we have relatively low p-values for both. We get a lower p-value for when the lot size acts as a dependent variable. But either way, they do both pass. Now, intuitively, we want to still use price as a dependent variable because when we're forecasting values in the future, now we're not going to, this isn't forecasting, this is more of a regression analysis, but when we do regression analysis, we kind of perform that to forecast values in the future. And when we're forecasting values in the future, we want to focus on the price of the house, not the land size, because the land size we already know, the house size doesn't change over time, but the price does. So intuitively, we're going to use price as the dependent variable. Price acts upon the lot size. Obviously, over time, obviously price isn't going to change over time based on the lot size, but just for future practicality, we want to use price as a dependent variable. So next, what I want to do is use a reset test. Now, these arguments of power is what we're multiplying the multiple regression to. So if the multiple regression we regressed over here, if I, square all these values, not square, powered all these variables by 2, that's what we're testing for over here. If I power all those variables by 3, that's what we get here. And so looking at the results, we want to focus on the p-value again. The p-value, as we increase the power, will get smaller and smaller. Now, what does that mean? P-value getting smaller and smaller on the reset test means we'll reject we have further evidence to reject the null, but the null is saying this this functional form that we're testing for is okay. So the lower the p-value of the reset test, it's essentially saying we don't want to use that function. So the power of 2 looks fine, but if we use a reset test of the power of 1, we will get a perfect p-value of 1. So in this case, we definitely don't want to use anything over 2 to the power of 2. We can potentially use the power of 2, but for now, we're going to use a simple linear functional form for all variables. Okay. Okay, my bad. So this is the type fitted here means we're resetting to a functional form of the y value, of the y value within the multiple regression. So this multiple regression here, we're multiplying the power of 2 and 3 for price, not these variables. In this type regressor, that's what we're doing for the independent. So again, we have these very small p-values for this type regressor, and so we'll conclude that we want to use a functional form of 1. All right. So here we get to the part where we're basically testing for different functional variants. These functions, I don't exactly know like explicitly what they're trying to do. This forward is just a method. If we write backward, it's not very important. But if we just look at the results alone, we see that we have L for lot size, B for bedrooms, and D for driveway. And these two functions, what it did is it regressed all of these variables onto price, just the lot size in bedrooms and the lot size. And so when we do that, we obtain some of these values that honestly I don't know what these are representing, but for now we want to focus on the BIC. I believe this is also the CP or AIC, but I'm going to choose to focus on the BIC for now just for simplicity. And so what we see that the lowest BIC value, remember that the lowest BIC value is usually the ideal. Same for the AIC in this case, but just the BIC alone tells us that the lot size, bedroom, and driveway is the most ideal compared to just regressing lot size onto price or just regressing lot size or bedroom onto price. So we're going to utilize all of these 3 explanatory variables onto price, but we want to know if we have to have put price to the exponent of 2, because what we figured out here is that when we reset test using the fitted for the functional form of y, the reset test actually passed. It didn't go under the 0.05 threshold, so we want to try squaring the price by 2, multiplying the price by 2, and we get BIC values. We leave the explanatory variables the same because we want to compare it to the former regression values, regression variable. And so clearly we got a negative 251 BIC value, but when we regressed it with y squared, price squared, then we don't get a low enough BIC value to surpass this BIC value, which means we actually don't need to power price by 2. So right now we tested for the regular multiple regression model that we were using the whole time, except we found out that just prices should be preferred over the price powered by 2. All right. Using the log linear log, remember that the log linear is when we log the y, and linear log is when we log the x. So log y is usually to the left. In this case, log is usually to the x variables are usually to the right. So linear log, log the explanatory variables, log the y variables. Starting with the log linear, we keep seeing the BIC values. So looking at the BIC value, this actually surpassed the original model of negative 251. So we just conclude that this is preferred because we have a lower BIC value, than the original. The ASC value is the same, but I do think that a BIC differentiation of 20 is significant enough. Usually, if it's by 1 or 2, then we want to make other sort of tests to see which form is ideal. But we'll we'll conclude that the log linear is superior to the original regression model. All right, linear log. Again, looking at the BIC value, we don't get we get a similar BIC value to the log linear, um, same CP value. And so what I've concluded that we should do is, all right. So before we make a decision between what's preferred between linear and log linear, I've also regressed both the x and y, so log, and we actually do get a BIC value of -300. So that's the model that we're gonna use. Yeah. So now we want to test for multicollinearity. Remember that multicollinearity is when explanatory variables are correlated with each other because they're usually too similar. So in our example, if we have log of lot size, which we kind of interpreted that as land size, if we also have like acres, then they would have multicollinearity. Like we don't really need to check for that. Like they will have multicollinearity because they are too similar. But to check for multicollinearity, we want to use the VIF function for the regression model. It'll check the multicollinearity of each variables. Now I forgot to tell you, but we didn't log the driveway because driveway is just a binary variable of 0 and 1, so there's no point of logging those, these binary independent variables. So we don't include log in our, we never want to log our binary variables. But anyway, when we use the BIF for the log model, because that was the most ideal based on the BIC, we find out that none of these have multicollinearity because a high VIF value which means the higher VIF value means it is more of a concern for multicollinearity, and usually around 5 or more is when we get a concern for it, which all these values are around 1. So multicollinearity is not a concern. Intuitively, this makes sense because driveway and bedrooms and land size are not similar at all. They're all kind of different representations of a house or aspects of a house. Again, if we had like a driveway or like a garage, then we will be concerned for it, but it makes sense why we don't have any multicollinearity. All right. I've also, if you remember, I've also mentioned something about interaction variables. Remember that interaction variables are when we multiply 2 or more, we'll do 2 in this case, but 2 or more independent variables. I don't know if they can also be dependent, but dependent will probably cause too much collinearity. So multiplying 2 independent variables together as part of one explanatory variable. So what I did here is I've multiplied the log of lot size times the logarithm of bedrooms, as well as the logarithm of lot size times the driveway, and then log of bedrooms times the driveway. Lot size times driveway, and then bedrooms times driveway. So when I use a summary HH function for all of these, we get 6 different results of some of these variables being omitted, and then basically what this function is doing is it's testing for like all of these possibilities of the which independent variables are necessary, including the interaction variables. again, we would check for the lowest BIC. Now these BIC values in this case are very similar, and what you'll also notice is the CP values aren't exactly supportive of the BIC value, because the lowest BIC value is the third model being this regression here. It is kind of hard to see with like these very unclear acronyms, but I've analyzed it, what these symbols mean over here, so you can quickly take a look at that. But these are the two, I believe I wrote down two regression models here. One of them is the lowest, has the lowest CP value or the AIC value, and then the other one has the lowest BIC value. And so what I'm going to use to determine which of these two functional forms should be preferred is I'm just going to check the adjusted R-squared, because if you recall, that's our third indicator of choosing our model. It was the AIC, the BIC, and the goodness of fit. So I called the summary of each of these regression models. I checked the R-squared. First one is 0.431, so a little less than half. And the next one is 0.4419. The third one, or the second one, having much more explanatory variables. So it's not much of a difference. You know, using further analysis, we might eventually determine that the first model, the one without some of these interaction variables, is preferred. But what I'm going to conclude is the second model with all these interaction variables are preferred when it comes to determining the house price. So yeah, we included interaction variables of all variants. So lot size of bedroom times bedrooms, lot size times driveway, and then bedroom size times driveway. All right. Okay, so apparently what I wrote is we also have lower p-values compared to the first model, which is clearly correct, because some of these p-values are way too high. So yeah, what we basically did in this video, I'm not exactly done. I want to make some more analysis, but is we use all of these like BIC, AIC, R-squared, reset tests, and interaction variables to determine the ideal model. And what I want to emphasize is that there's no like correct way to like systematic way to like determine this. Sometimes you can use a reset test first, and then use like these like interaction variables, and then you can find the BIC. It can get a bit messy, which, you know, it's better in a way where we kind of use our intuitive sense, and we kind of it's not very clear. So in a way, it's more you become more curious of what the exact determinants of a binary variable is, but it's also very difficult. All right. So before I end this video, I want to. All right. We also need to test for heteroscedasticity. This is a long video, so I want to kind of wrap it up quickly, but all right, actually, what I'm going to do is end it here, and then I'll make a part 3 of this multiple regression, because this is turning out to be a longer video than I thought. So I'll see you guys there.